Reasoning models pay a hidden tax. Every extra step of thinking triples your memory. On a 32,000 token generation, Oro burns about 28 gigabytes of VRAM. Melt does the same iterative reasoning in under 10. How can a model loop its layers 4 times and somehow keep one cache the same size as a model that never loops at all? There are 2 ways to make a language model think harder. You can let it talk to itself, generate more tokens, more reasoning, longer chains of thought. Or you can let it stay quiet and just run the same layers again, and again, and again. The first costs you output length, the second costs you something less visible. The paper puts it bluntly, looping the layers makes memory grow with reasoning depth, linearly. And that memory lives somewhere very specific. A standard transformer stacks n layers, 1 pass, 1 prediction. A looped transformer, like Uro, runs the same stack again and again. T iterations, same weights, more compute. 1 forward pass becomes T forward passes through the same composition M. Now, where does the KV cache live? Inside every layer's attention, every token deposits 1 row, its key, its value. The next token attends to all of them. For 1 forward pass, n layers, L tokens, the cache is a flat sheet, n times L rows. Now loop the stack 4 times. Every loop appends a fresh row at every layer, at every token. The cache becomes a box, not a sheet, a box. Here is what that box weighs. At 32,000 tokens, Uro's KV cache alone, 25.17 gigabytes. Its model weights? Under 3. The cache is nearly 10 times bigger than the model itself. Qwen, a standard non-looped model, 3.67 gigabytes. Melt, 6.29. Uro, 25. For long reasoning, the cache dwarfs the model. This is why you cannot just keep adding loops. So Melt does something simple to say and tricky to make work. 1 KV cache per layer, shared across every loop. The size of the cache no longer depends on how deep you reason. Think of it as 2 scratch pads. Uro takes a fresh sheet for every loop and never throws any of them out. Melt keeps 1 sheet, erases, rewrites, in place. That collapses a 3-dimensional cache back into 2. But it raises the obvious question. If you only keep 1 cache, how does it remember loop 1 by the time you're at loop 4? Melt learns a gate, 1 per latent dimension, call it Z. Z is a sigmoid of an affine function of the new input and the old state. And the update is GRU style, a per-dimension convex combination. When Z is 1, keep the old state. When Z is 0, overwrite with the new input. In between, a smooth crossfade, dimension by dimension. You might ask, why not just average the loops, or take the last one? The paper tries every shortcut. All of them drop 15 points on the hardest math benchmarks. The learned per-dimension gate is doing real work. Project the latent state through WK and WV, and you get the 1 key, 1 value that everyone attends to. That single, gated, rewritten row is the whole Melt trick. A clean architecture, That on its own will not train. Melt's per token update is sequential. Each token's gate depends on the last. So fine-tuning happens in chunks. Trade some parallelism for fidelity to the loop dynamics. And the architecture swap? That's a crossfade, not a cut. Phase 1. Mix the new Melt key value stream with Uro's original, weighted by alpha. Alpha climbs from 0 to 1. The model inherits Uro's behavior, then slowly drifts toward Melt. Phase 2 locks in what was learned. Freeze Uro, use it as a teacher. At every layer and every loop, pull Melt's post-attention output toward Uro's. The loss adds a distillation term averaged over all n layers and all t loops. And one number sells the entire training recipe. Remove chunk-wise training, keep everything else. Accuracy on every benchmark, 0.0. The recipe is not optional, it is the paper. So, does the architecture earn its keep? This is the figure that lands the trade-off. AIME26 pass at 1 on the vertical axis, memory at 32,000 tokens on the horizontal. Standard models live on the left, cheap memory, lower accuracy. Uro lives on the right, high accuracy, brutal memory. Melt sits in the corner that used to be empty, cheap memory, looped model accuracy. Across the math benchmarks, AME, AMC, Math 500, Melt beats every standard transformer its size. It is a hair behind Uro on the hardest sets. Uro keeps 4 times the memory. Melt keeps roughly the memory of Quen. Looped model reasoning, non-looped model memory. 3 honest caveats. 1. The number of loops is fixed at inference, no adaptive depth. Yet. 2. Melt does not use multi-query attention. Quen still wins on raw memory by a factor of 1.7. 3. Training is still sequential across tokens. Chunks help, they are not free. Scaling a language model used to mean making it bigger or making it talk longer. Melt lets it think longer, inside its own hidden state, at fixed memory.